Hi students, in this video we'll discuss few definitions. First, what is alphabet? Alphabet, as I said, if I take English as a language, I have a set of 26 symbols as an alphabet. Right? So alphabet is a finite set of symbols. So the notation for this alphabet is sigma, and here sigma equal to A, B, C, D. So I have 4 alphabets, right? A, B, C and D. What is string? I can coin the symbols from my alphabet to get a string, right? So string is a finite sequence of symbols taken from sigma, right? I can coin the symbols from sigma to get my word or string. Then what is length of the string? The number of characters in my string is known as the length of my string. Right, the notation for this length is this modulus character. And empty string I can denote using lambda or epsilon. Mostly I'll follow this epsilon. Then what is clean star? Right. So if I want to do repetition, if I want to repeat a string, I can go for clean star. Right. So star. Sigma star is a unary operator on a set of symbols or strings that gives an infinite set of all possible strings. Right? It is repetition. I can repeat for infinite. So it gives you an infinite set of all possible strings. I'll tell you. Suppose if I want to find A star, right? The meaning is null or more occurrence of A. This star includes empty string also, right? So how I can denote empty string? Using my epsilon, right? So star includes, star means null or more occurrence. So A star means I can have null or a single A, 2 A's, 3 A, 4 A and it goes on. So sigma star means, what is sigma? Alphabet. Star means all the alphabet symbols for more occurrence, 0 or more occurrence, right? Here in the example they have given like A comma B. So I have 2 symbols in my alphabet. So I can have an empty string or a single A, 2A, 3 A's and it goes on, or single B, 2B, 3 B's, it goes on, or I can have a combination of both the alphabet symbols AB, BA, AAB, BBA, like that. It will be an infinite set of all possible strings. Right. Next is clean closure plus. Right. So first we have seen this star. In star I'll have null. In plus I won't have null. Right. Plus is one or more occurrence. Star is null or more occurrence. Here plus is one or more occurrence. You can see I won't be having this empty string or null string. Single A, single B, double B, mixture of A and B. Right? A, B, B, A, B, 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 A. It goes on. Right? You can see sigma plus is equal to sigma star. In that I have to eliminate my empty string. Language. Language is a subset of sigma star. Right? A language is a subset of sigma star for all possible alphabets. Right? So as I said in the previous video, my finite automata. Right? So what is finite automata? My model should have finite number of states. Right? Automata is self-acting model. This model should have finite number of states. So this finite automata is divided into 2 main types, that is DFA and NFA. Again under NFA I have NFA with epsilon transitions. DFA is deterministic finite automata. NFA is non-deterministic finite automata. And the third one is non-deterministic finite automata with epsilon transition, right? So what is the meaning of this deterministic? Deterministic, for each input symbol, one can determine the state to which the machine will move, right? So input symbols will be given in the notation sigma. Input symbols is nothing but all your alphabets, right? So one can determine the state. So if a state takes an input, it will move to any one another state. I'll tell, see this here, by seeing this diagram I can understand input symbols are 0 and 1. I'm not having more than that. I have only two input symbols. I have only two alphabets, 0 and 1, right? So each state will take both the inputs, right? See here, this is my first state. It is taking 0 input and staying in the same state. And here it is taking 1 input and moving to the other state B. Deterministic means when it takes an input, it will move to only one state. It will not make multiple moves, right? If it makes multiple moves, it is non-deterministic automata. Suppose, right, here, when state A takes 1 input, it is staying in state A and it makes a move to state B, right? Same input, it is making 2 moves. For same input, if it is making 2 moves, it is not a DFA, it is an NFA. For a single input, if it makes only 1 move, it is a deterministic automata. That's what it is written here. Determine the state to which the machine will move. For each input symbol, one can determine the state to which the machine will move. It will move to only one state. It will not take multiple moves. So it is known as deterministic automata. And it has finite number of states. So deterministic finite. The machine is called deterministic finite machine or deterministic finite automata. So if it makes multiple moves, easily you can identify that automata is a non-deterministic one. Right. The DFA is represented by diagrams called state diagrams. The state diagram will have vertices represent the states, right? Every circle represents a state. The arcs labeled with the input symbol shows the transitions, and the initial state is denoted by an empty circle, incoming arrow, right? Incoming arrow, right? And the final state is indicated by double circles, right? This is your diagrammatic pictorial representation of my automata model, right? State with an incoming edge is start state, right? Double circle denotes final state, and edges with labeled input is known as transitions, right? And every circle represents a state. And as I said, see, I told every model will have a language associated with it, and language will have its own grammar, right? The language associated with finite automata is known as regular language, right? So when a language is given to a model, and if it could recognize that language, I can say it is a regular language. There are some languages where my automata cannot recognize those language, right? So for such type of languages, I should move to the next model, right? I told in the previous model, I have many models like push down automata, finite automata, linear bounded automata, Turing machines, right? I have many models. So when a language is accepted by a finite automata, it is known as regular language. If it is not accepted by finite automata, I should move to the next model. I should check with that whether it could accept that corresponding language or not, right? That everything will elaborate clearly in the further videos. Thank you.